Swayam Prabha. Digital India. Educated India.
Example, what you may come across in your textbook is cycloaddition reactions. How many of you have studied this? Diels-Alder reactions. You studied this? Yeah, what is that? Diels-Alder reaction. Another partner, which is a dienophile, you get a cyclic structure. This also involves simple electronic rearrangement where you have two reacting components. There you have two reacting components. Here there is only one reacting component, right? Cycloaddition reactions or addition reactions. You have two fragments, they add together to build a molecule. Nothing is lost. It is highly atom economical process. You have four atoms containing hydrogens. Another component comes in, right? Dienophile. It has two carbon atoms and the associated atoms with itself. They just add. No atoms are lost. So it is highly atom economical, and this is another class that we are describing here, which is a class of pericyclic reactions. Okay. So all the other examples now you should be able to correlate via pericyclic reactions, which is electrocyclic reactions. In this case, it is a spiroxazine structure. It also undergoes a ring opening at this site, right? Creates this zwitterionic species. You can also write it as a quinonoid form. So you can move these electrons, right, the negative charge all along, and you will find that you will get a double bond here, you also get a double bond here, you also get a double bond here, and so on. You can, move these electrons. You find that you will generate a myrocyanin species which is also colored. Okay. Here is another example, dithionyl ethene. There are two thiophene molecules put in there, sulfur containing molecules, right? That was pyrrole we said. With nitrogen, there is thiophene here. And when you shine light, they also undergo the 6 pi electron. You see, it is converted to 4 pi system. One of the pi electron is getting transformed to a sigma bond. So you generate a dihydro intermediate. If you look at this structure, it's going to be completely flat, unlike this structure, right? Because they have crowded methyls in between. So you break this conjugation, this is colorless. You start from a colorless species to generate a colorful compound. Likewise, various systems are designed purposefully. Okay, implying simple electrocyclization reactions. What we are going to talk about today is only this molecule. Yeah. Why is it called? Which is an intermediate? Yeah, dihydro intermediate, because usually it is a derivative. What is shown here is a methyl derivative. Let's say you don't have the methyl. What you will have is a compound to begin with hydrogens. At the end also we should have hydrogens. Now when you have hydrogens, there is a possibility for it to undergo photochemical oxidation, further giving you a completely aromatic compound which ultimately stays like that, will not be reversible. Now by arresting this, to arrest that side reaction, which is a photochemical oxidation, what you have put is the methyls, right? And now it stops here because hydrogens are not there for it to undergo oxidation. So it stops at the methyl stage. Now you can play with this structure, allow it to function back and forth. So photochemically you can operate it on and off switches. So that's why it is called the dihydro intermediate, because it derived from the parent dihydrogen containing compounds. Okay. Otherwise it is just a species which you are generating from A to B and B goes back. Okay, so I forgot to tell. This is the particular example that we are going to discuss, which is the benzopyrens. This also undergoes a ring opening at this site. It undergoes a carbon-oxygen bond cleavage when you shine it with light. You can look at the bond energy of carbon and oxygen, CO bond, CO single bond. You will find out the wavelength, what is the wavelength that you may want to use to cleave that carbon-oxygen bond. Shine with that wavelength, you can cleave this bond, opens it up, gives you this kind of a species. Okay. So this can again, if you just switch off the light, it would come back to this form. But naturally, if you are looking at the structure, can any phenols be colored? Phenols. Benzene, colorless. You are attaching hydroxy group onto it, becomes phenol. Is phenol colored? Phenol is not colored. It's not supposed to be colored. If you store it over a period of time, you may get a pink color for the phenol. Doesn't mean that phenol is colored. It undergoes photooxidation again, right? So this is a phenolic derivative. So this should also be colorless, right? So in principle, if it undergoes a ring opening, that also will not be colored, but there will be some spectral changes that you may notice in the ultraviolet absorption spectrum, right? The main drawback with this system is that you are disturbing the aromaticity in this case. So the species that you are generating is very short-lived. Right? So you may ask me, sir, what if I lower the temperature? Can I make the resultant product stable? Lower down the temperature, can I trap this product? People have tried it up to minus 100 degrees centigrade. This orthoquinoid species remain unstable at minus 100 degrees. Okay. So what is the next strategy that people have come up with? They have started putting one more benzene ring to this. So instead of benzopyran, how do you call that? Naphthopyrans. Right? So you are making an annulation, benzoannulation here, or here, or here, doesn't matter. But you put one more benzene ring to this benzopyran. The resultant compound is colored and you can observe the color that is generated. Now how will you explain it? This is not colored, but the moment I annulate it, I make it as an naphthopyran, that is colored. How can we explain this? In that case also you will destroy the aromaticity of one ring. Correct? But the other ring is not losing the aromaticity. So that gives to some extent the stability for the system, and hence you can do the color change, reversible color changes back and forth n number of times. So people have adopted to annulation strategy to make this compound colorful even at room temperatures. So those derivatives are called naphthopyrans. Now I think I must have to move faster. So just to give you a brief introduction on these electrocyclic reactions, like we saw some of the systems undergoing electrocyclization, right? So it's a quick overview. Start from cyclohexatriene, very basic system without all the decorations, peripheral decorations, right? It's a very blank system, plain system. Start with 1,3,5-hexatriene. You can thermally cyclize it. You can also photochemically cyclize it to give you 1,3-cyclohexadiene systems. Started off with a triene, you generate a diene. What has happened in the process is you have converted a pi bond to a sigma bond, right? You can also do this on a butadiene system. But the problem with the butadiene system is when it undergoes electrocyclization, you get a cyclobutene losing one pi bond, generating one sigma bond. So there is a compensation. What you see is you are generating a cyclobutene, but this is a strained system because of the four-membered ring that it has. It has only 4 carbon atoms. Not only 4 carbon atoms, it also includes one carbon-carbon double bond with itself. Right? What if you have a carbon-carbon double bond inside a 4-membered ring? That could be your question. If you are looking at carbon-carbon single bonds, right? If you look at this 4-membered ring, it will appear like this. This is the base. It appears like this. A typical tetrahedral angle is what? sp3 hybridization. These carbons are now, all of them are sp3 hybridization. For a methane, typical methane, 109.5 or 48, whatever. So this one, what is the carbon angle here? Carbon angle. It should be 109, right? What you are having here is 90 degrees. So it is relaxed when it is 109. You are pushing it to come to 90. Obviously, it feels the strain with itself. What is that strain called? It's an angular strain that is imposed onto this cyclobutanes. Is that the only strain you look at for this compound? Any other strains you notice for this molecule? I just want to throw in between some lights so that when you read you will connect. Any other strains that you look at in this molecule, you can find in this molecule other than the angular strain that we talked about? What else are the other parameters that can give this molecule a strain? Hydrogens? Answer is correct. Why? There's not much space between the hydrogens. Which hydrogens you are talking about? Two hydrogens, which hydrogens? Between these two hydrogens? Or this hydrogen and this hydrogen? Which hydrogens? This and this? Or this and this? This and this?
These two can rotate because the electronic flows from the other.
These two can rotate. How do they rotate? If they should rotate, they should rotate along this axis. Right? That's the only way that it can do. So what is the strain there? I understand what you want to say. Let me put it, you correct me, okay? So you have this 90 degrees carbon bond coming together to make a 90 degrees. Because it comes, the hydrogens that are sitting behind me would also adjust itself, right? Some deviation from it. Because I am stretching like this, the hydrogens that are sitting behind me would also undergo some kind of a arrangement to balance this change with the CCC, right? So there is some change with this. So when you are talking about this angular strain, you will also have an angular strain associated here. That is also an angular strain. So we are still talking about angular strain only. What is the other factor that you think could be responsible for causing the strain? They can go back, they can come, so it's all doing that. Other than that, any other strain that you can notice? Because you may be studying conformational analysis at some point. Torsional strain. Who said that? Good. What is the torsional strain you are looking here? It can't really rotate because it's a cyclic system. They are locked together, right? So now, what is the torsional strain you are talking about? Torsional strain between? Say it again, loudly. Carbon and carbon. Oh no, I wouldn't say that. Torsional strain, the answer is correct. But that is between the hydrogens that are here and here, here and here, here and here, here and here. Why am I saying this? You take this bond, this particular bond, where these two hydrogens are attached with each carbons. I just move it like this. So you need to have a three-dimensional view. Now there is a carbon at my front, sorry, at the back. There is a carbon at the front. I am putting it in one axis. You are seeing through this bond, okay? You are seeing through this bond. Now what happens? The behind carbon represents this. The front carbon is this. Now how am I supposed to draw the hydrogens attached to them and the carbons? So the behind carbon, let's say its bond is like this, right? The front carbon, color chalk. The front carbon also has a bond like this. They are exactly overlapping one on top. The hydrogens from the behind carbon are attached like this. Right? The hydrogen from the front carbons are attached. You must have studied eclipsed interactions. You studied or not? So can you see an eclipsed interaction here? Right? I have drawn it in assuming it is so perfectly 90 degrees. But they are not. They don't like these eclipsing interactions. Keep in mind. Right? Instead what they do? They want to go for the stagger. But it cannot. Look, these two ends are tied. You are not allowing the molecule to be free to decide on its own. So how will they be able to get the staggered conformation? No way. But it would get as much as it can. So in a stable conformation of cyclobutane, you will see these hydrogens are slightly away. It's not exactly overlapping one on top, but they would slightly be away. Right? And hence it is not perfectly a square. It would be slightly, one carbon alone will just jump up from the plane. Jump out from the plane. Okay? So there is a small deformation in the cyclobutane. Now you understand the strain in this system. So how many of these torsional strains are there in this molecule? Eclipsing interactions. Huh? 4. 1, 2, 3, 4. How about these 4 hydrogens? So you have 8 eclipsing interactions in total. Okay, which the molecule doesn't like. So it deforms to an extent that it can, little bit, because only 4 carbons and they are tied, not much freedom available. So this is strained. Now let's come to our story, where we said there is a cyclobutene, right, formed in the process. What have you done now? You made the molecule go mad actually, right? You converted to sp3 to sp2. How much does that angle require? How much of an sp2 hybridized carbon would require? 120. So from 109 to you have further strained it to 120. Man, it is really struggling to achieve this 120 degrees. It is logged into is 90 degrees now. How much is the strain that this molecule would undergo, right? So that is why if you start from cyclobutene, 1,3-butadiene, cyclize this to get cyclobutene, yeah, maybe 10% you would get converted to this. As soon as it is formed, it would immediately open up and come back. So that is why the backward reaction is more than the forward reaction. So if you are starting with cyclobutene and then shine light, you will be able to just like that do the ring opening. Because it just molecule is waiting to release its strain. Moment you impinge the appropriate wavelength on top of it, that's it, it's gone, it would open up, immediately give you the cyclobutene. So the backward kinetics is faster than the forward. But in the case of cyclohexatriene, you are making the stable form already. It's a 6-membered ring, it's quite stable, it can accommodate, and hence the backward reaction also is slower. So making the appropriate kinetics for such systems are very demanding. You can achieve the color, but from color to colorless state could be challenging. So that's why a lot of interest is in this area. So color development, all these things are important for a material. This is what I was telling you. When you have naphthopyrens, usually observing the colorful state is very difficult even at minus 100 degrees. So how do you stabilize it? How do you generate a stable colorful molecule that you can observe was the question. People have tried to annulate it. You can do a Benz annulation. So you create naphthopyrene, several different isomers, and you can create this naphthopyrene. When a ring opens, you will see that one ring remaining aromatic. That keeps the molecule, the ring opened molecule, stable. And this species is colored, right? You can see the absorption coming in the visible region, 400 nanometers. You can conveniently record ultraviolet absorption spectrum, not at 100 degrees. You can do it at room temperature for these naphthopyrens. So what you basically do is you take a pinch of this compound, naphthopyrens, put it in a solvent, which is okay, which is available. Most often we use a non-polar solvent to do this job. Dissolve it, kind of toluene or whatever. Dissolve this compound, shine it with the ultraviolet light. If it absorbs in the ultraviolet region, if it is colorful, absorbing the visible region, color 1, then you shine light of appropriate wavelength. Then the molecule absorbs, gives you a new absorption band in a farther region, right? And you can irradiate the newly generated species using the wavelength where it has absorbed. Then you can revert it back to the colorless form. It is in solution state. You can do these measurements in solution. People have also demonstrated, yeah.
Beginning of the class, they explain like applications. So that when the sunlight hits the glass filament, it becomes colored, and then when the sun goes that way, it becomes like normal and that. But then in the absorption spectrum point, the compound B, that is the colored compound, that is both UV as well as visible. So when the UV, you said when the UV hits, it will go back to A and then will again go back to B. So when the sunlight, so like we have the colored material, when the sunlight hits, it will first become colored compound B, but then sunlight also contains a certain amount of UV radiation. So won't it just flicker back and forth A and B?
When the sunlight is going to the other end.
No, not the other end. So you have the material and then you put in sunlight on it. Sunlight does not only contain visible light, it also contains UV. So
correct.
Won't it just flicker back and forth rather than just staying that and then staying as color?
It would. You will have a population of the B and A at that point. But how much you want to achieve is something the engineering of the molecule does. Okay. In this case, I am showing you one particular product. You can look at these wavy bonds that is shown there. That is the cause for other isomers that can be generated in the medium along with your starting material. Okay. So you can have some population of this because always this one would come back here. But if you can make this reversible process slower, that means probably you will have, let's say, 5% of this in the 95% of this species existing. So they coexist to some extent. That is for sure. Yeah. Okay. So people have also shown it in solid state. You crystallize this compound. You have a colorless crystal to begin with. Shine light onto the crystal. Now the whole crystal undergoes a color change. Okay. So can you imagine this? How do you visualize this? In crystalline state, molecules are organized and they have very less freedom, right? Because they are packed close together, one over the other and so on. So they very small gap available surrounding itself. In that condition also, you can do this transformation of colorless to colorless state. So gap, how does it come into picture? You are converting an sp3 hybridized carbon to an sp2 hybridized carbon. This is more of a planar character. It has to ring open, right? This bond has to cleave, isomerize and go to the other end to give you this isomer. So you need a large volume in the crystalline lattice surrounding a particular molecule, right? Only then crystalline state photochemical transformation could be possible. But it looks like for this compound, you have the necessary void space surrounding this particular molecule, and it can undergo a ring opening to give you a colored state. Okay, so you can also do the reversible process, which is not shown here. I don't want to talk about it in detail, but what I can tell you is photochemical excitation is very fast to process. How much fast it was, we said? In few femtoseconds. Molecule goes to excited state, they don't even realize that they are there because nuclear displacements are none at that point of time. It starts to happen after a while, right? So first photochemical excitation happens in just 450 seconds, they are gone to the excited state, then there is a cascade of things that are happening. You will populate these isomers that we saw, B1, B2, B3 in all these cases. What are those isomers? Those are these isomers that you can have in the solution. If you start with pyrens, you can get isomer 1, which is called schizoid cis. This schizoid cis can transform to transoid cis, which is TC. Then it can again isomerize to transoid trans. It can also come back to schizoid cis and so on. So what is this schizoid cis? What is this transoid cis? What is schizoid and transoid? You guys know about it? You guys have studied about it? Schizoid, transoid. Yes cis, yes trans. Yes cis, yes trans. You studied this or not? No? Cis trans isomers alone you have studied. Okay, when you talk about dienes, butadienes, have you come across this yes cis, yes trans conformations? No? So you can have two forms when you have dienes. You can draw the olefins, right, across the single bond like this, one way of drawing it. Another way is like this, right? I can place the olefins like this, I can place the olefins in opposite directions. So this is across the single bond. So across the single bond conformations, yes, across the single bond, both of them are in cis fashion, same side of the single bond, call it as cis, and this is yes, across the single bond, both the olefins are pointing opposite directions, so it is trans. Yes is what? Across the single bond. Okay. So yes cis and yes trans. These two are the conformations. This is conformations. These are not configurations. Cis and trans are configurations or conformations. They are configurations because they cannot be, you cannot just like that rotate a double bond and then make a trans. It's not possible. You need light to do that because that much energy you need to provide by light only. So this is conformation because rotation, it is just a rotation, right, across this single bond. So this is a conformation actually. It is me, I have my hands here. So I can be this, I can show like this. These are conformations. It can come back to its natural position, right? But if I take this hand and put it here and take this hand and put it here, that remains a configuration. It's not possible, right? So this is yes cis and yes trans. What you are having? So this, if anywhere you see this unit, you call it a cissoid unit. You take this unit, you will look at any structure, you look at this unit, it is a transoid unit. And that's what it is shown here. You have a cissoid cis, right? Well, can you locate the cissoid cis here? What is the cis double bond? This is the cis bond here. This bond is cis and there is a cissoid here. Transoid cis. So this is again cis This bond alone you look at, that is cis. But transoid is this. Okay. Similarly, next structure which is trans, the middle double bond. You have one unit going up, one unit coming down. That is a trans. It was cis there. Both of them are coming cis. Here it is trans. At transoid, it still remains as transoid. Here, this becomes a cisoid. This is a trans double bond. With respect to the central double bond, you look at. So these are the 4 isomers that you can generate by photolysis. Okay. So this is all these things coexist in the solution. Moment you shine light onto the molecule. But what can happen to each of these isomers? Some isomers may live longer. Some isomers may live shorter, depending on the environments that they face in the solution when they are generated. So in these cases, if you look at this isomer and this isomer, these two ends are very close. As soon as it is generated, they can undergo ring closing and then go back to the starting material, this ring closed isomer compound. So it is a short-lived species. This species, if you look at, you have the phenyls attached to them. This you will face with the hydrogen, there is a hindrance. So they will not be able to stay in this form. Immediately they would come back to this form or that form. It would remain in these two forms. So what are the two short-lived species? This and that. What are the long-lived species? This and this. So the color is mainly due to these two isomers in the solution. You can do this by lifetime studies. You can look at the species individual lifetime. You will see some of them decay very fast than the rest. So you will know the fast decaying species are due to the short-lived isomers in the solution, and if a species decay is very, very long and its lifetime is long, decay is slow and it has a very long lifetime, meaning that that is responsible for this. Okay. So anyway, I stop here. The next speaker is here. I should not eat up his time. So I will welcome Professor Somnath and take over this session. Okay. So I stop here. We can continue some other time. Right. Thank you. You really have, okay. He's waiting. Sir has come already.
I feel extremely privileged and honored to avail this opportunity to present the vote of thanks to Professor Swayam for taking time off his schedule and coming here to interact with us and give us such an amazing amount of presentation on photochromism and its various aspects. It's already a short-living topic. So thank you so much, sir. I would also like to thank the RSS management and the technical team for ensuring this more productive. Thank you. Thank you.